operators and expectation values in quantum mechanics. In quantum mechanics, observables, which are just things that we can measure, are represented by operators, which are useful mathematical things. And the observables are chosen, or they're defined, to satisfy a commutation relation that the operator for position applied after the operator for momentum minus the operator for momentum applied after the operator for position is equal to I times h bar. And this statement is a basic, unprovable, underivable postulate that is useful because it fits with measured reality. I'm sure many of you have seen this before as the Heisenberg Uncertainty Principle. So again, x here with the hat is the operator for position. It's the mathematical expression corresponding to the physical property of position, and p hat is the operator for momentum. So how can we choose our operators? How can we write down mathematical expressions for x hat and p hat so that they satisfy this commutation relation, so that they're consistent with this Heisenberg Uncertainty Principle? Well, one way that we can do it is to choose the operator for x to be just the operation of multiplying by position in the x direction. We'll just write that as multiplying by x. That's a sensible choice for an operator corresponding position to position. If we do that, then we no longer have a choice for the operator for momentum. We'll prove this in a minute, but with this choice for the operator for position, the operator for momentum is required to be minus I times h bar times d by dx in order for the Heisenberg Uncertainty Principle to be satisfied. That looks perhaps a little less intuitive than multiplying by x, but this is a requirement to satisfy the commutation relation. Let's quickly check that this works. So let's first work out what happens when we apply first the momentum operator, then the position operator to some general wave function psi. This is just the position operator times minus I h bar d by dx, acting on psi, which is minus I h bar, the position operator is just x, times d by dx, acting on psi. So that's this first term in our commutation relation. If I now calculate the second term by operating with momentum after I operate with position, it's actually a little bit more complicated. My momentum operator then operates on x times psi, substituting multiplied by position for the operator, the x operator, which is minus I h bar times d by dx of the product of x, and let me write out explicitly that the wave function is a function of x, so that I see I have to differentiate by parts, and I get minus I h bar x d psi by dx minus I h bar psi dx by dx, which is just 1. Then I can subtract these two quantities, and I see immediately that I obtain I h bar times psi. So with the choice of the operator for position being multiplied by position, then my operator for momentum is required to be minus I h bar times the derivative with respect to position. Once we have our operators for position and momentum, we can construct operators for all dynamical variables. So for example, the kinetic energy, which we know is p squared over 2m, then the operator for kinetic energy is the momentum operator squared over 2m, which is minus h bar squared over 2m d2 by dx squared in one dimension, which of course we're familiar with as the kinetic energy term in the Schrödinger equation. So that's the concept of a quantum mechanical operator, the mathematical thing that will correspond to a measurable thing, an observable. The next concept we want to introduce is the concept of the expectation value. And when a system is described by a wave function, some general wave function psi, which may or may not be a solution of the Schrödinger equation. It does not have to be, this statement is more general than just for wave functions that are solutions of the Schrödinger equation. Then the average value of some observable it's called the observable omega, is given by the quantity which we call the expectation value. It's the integral of psi star times the operator corresponding to the observable omega times psi over all space. If our wave function wasn't normalized, we have to divide that by the integral of psi star psi over all space in order for the quantity to be normalized. So this denominator, we only have to worry about psi wasn't appropriately normalized at the start. And this average value of the observable is called the expectation value. And we often write it as omega in pointy brackets. So again, our notation, omega hat is the operator corresponding to observable omega, and omega in pointy brackets, which is the integral of psi star omega hat psi over all space, is the expectation value the average value of omega for wave function psi. Okay, let's look at an example then. And the example I want to look at is the particle in a box problem. And we'll look specifically at the ground state. And we'll work out the expectation values of the energy, the position, and the momentum. And so the problem is an electron confined in a box of length L between, say, x is equal to 0 and x is equal to L, with a potential 0 within the box and infinity outside of the box. And so the problem that we need to solve, our Schrödinger equation, is minus h bar squared over 2m d2 psi by dx squared is equal to E psi, because our potential is 0, with the boundary conditions that the wave function at 0 is equal to the wave function at L is equal to 0. So our wave function goes to 0 outside of the box. I'm going to write down the solutions. In this case, we're not going to work through this explicitly. But the wave function n is equal to square root of 2 over L sine of n pi x over L. for n any positive integer, and the energy is h squared over 8ml squared times n squared. You should make sure that you can derive this and solve this equation if it's something you're not so familiar with. Okay, so let's work out the expectation values. First, for the energy. Which is the same as the expectation value of the kinetic energy in this case, because we know the potential energy is 0. So this is equal to the integral of psi sub n star times the operator for the energy times psi sub n over all space, which is, let's put in the general expression for the wave function as a function of the n quantum number, and we'll set n as equal to 1 later, sine n pi x over L. The operator for energy is minus h bar squared over 2m d2 by dx squared. It's the operator for the kinetic energy times sine n pi x over L. Again, integrated over all x. I'll let you work out the details of the mathematics yourselves and simplify the resulting expression. And what you end up with is h bar squared over 8ml squared times n squared, which of course is exactly the same as the expression we obtained from solving the Schrodinger equation, because we're calculating the same thing. So this is good that we get the same answer. For the case where n is equal to 1, it's h squared over 8ml squared for the ground state. So this calculation, in a sense, didn't need doing. Once we've solved the Schrodinger equation and we've obtained the wave functions that are solutions to the Schrodinger equation, then the expectation values of the energies of those wave functions are the energies we obtained from solving the Schrodinger equation. Now let's take a look at the momentum. The expectation value of the x component of momentum is equal to psi n star times the momentum operator times psi n, which is 2 over L, integral over the box, sine n pi x over L. This time our operator is minus I h bar d by dx, operating on sine n pi x over L. Again, integrating over all x. Let me do one intermediate step for you, rearranging things a little bit. This is minus I h bar 2n pi over L. The integral from 0 to L. I can rewrite my sine cosine as a half sine 2n by x over L dx. And if you're careful, you will notice here immediately that this integral is just 0 by symmetry. It's a periodic function that is equally positive and negative over the range of the integration. And so you can write immediately that this is equal to 0 by symmetry for all n values, not just for the ground state. So our particle that's confined to a box, it's confined to be within x is equal to 0 and x is equal to L, and it doesn't spill outside of that, has 0 linear momentum, which of course makes sense intuitively because it's not going anywhere. It's confined and it's stuck in the box. Okay, the last one then, the expectation value of the position, x, is the integral of psi n star times the operator for position times psi n dx. Which is 2 over L times the integral between 0 and L. Here we can write the x at the front because it's just multiplied by x times sine squared n pi x over L dx, which is, let's rewrite the sine squared part as 1 minus cosine 1 over L, the integral from 0 to L, x minus x cosine 2 n pi x over L integrated over all x. My first term here this gives me L squared over 2. I have x squared over 2 between 0 and L. And then I have an integral between 0 and L of x cosine 2n pi x over L dx, which I can either integrate by parts or recognize by symmetry that immediately this is equal to 0. So my solution for the position operator is L over 2, again for all values of n, not just for the ground state. So the average position, the expectation value of the position, is halfway along the box. Now this is immediately obvious for the ground state, which we know is a sine wave that looks like this. The most probable position, the average position, we see immediately will be at L over 2. It's also the case for all the n values with the first excited state. Let's sketch that wave function, which has a node at L over 2. So it's perhaps a little bit less intuitive that the expectation value should be L over 2 in this case. But what it means is that the probability of the electron being to the left of L over 2 is exactly equal to the probability of the electron being to the right of L over 2. And so the expectation value is still L over 2 in this case also. Okay, the last thing I want to discuss then is just a little bit more formal. And that's quantum mechanical measurement theory. And quantum mechanical measurement theory tells us that there's a fundamental difference between cases in which the wave function is an eigenfunction of the operator for the observable of interest. And so what we mean by that, what it means to be an eigenfunction, is that the operator operating on the wave function is equal to some eigenfunction, some eigenvalue, times the wave function again. So this case where the wave function is an eigenfunction of the operator for the observable we're interested in is fundamentally different from the case where it's not. And in the case when the wave function is an eigenfunction, so in this case, then every measurement of the observable, omega, gives the same value. And the value that the measurement gives is always the eigenvalue, little omega. And so in this case, the expectation value is equal to the eigenvalue. In the case that it's not, if the wave function is not an eigenfunction of the operator corresponding to the observable that we're interested in, then different measurements give different answers. With the average value being the expectation value. So the very last thing I want to do then is just to look at these two cases mathematically. So let's take the simple case first, that the wave function is an eigenfunction of the operator corresponding to the observable that we're interested in. Then the expectation value of this observable is equal to psi star omega psi integrated over all space. And because the wave function is an eigenfunction, then the omega operator acting on psi gives us the eigenvalue, omega times psi. So our integral is psi star omega psi integrated over all space, which is omega, the integral of psi star psi. And if we're appropriately normalized, this is equal to 1. And so the expectation value is omega. And again, an experiment to measure the value of the observable omega always gives the result little omega, the eigenvalue. The second case is a little bit more complicated. The wave function is not an eigenfunction of the operator corresponding to the observable we're interested in. But in general, it can be expressed, it can be written as a linear combination of the eigenfunctions. And this last statement is rather profound, but it's in general the case in quantum mechanics because we have very well behaved, mathematically very well behaved operators with the property that they're Hermitian, which means that you can, in general, expand any function as a linear combination of the eigenfunctions. So we can write our general wave function as a sum over the eigenfunctions multiplied by some coefficient, where here the operator omega operating on f sub n is equal to some eigenvalue times f sub n. So I'm using simple f sub n here to represent an eigenfunction of the operator omega. But my wave function that I'm interested in, that I want to calculate the property of, isn't equal to one of those eigenfunctions. It's equal to a sum over many of them. Now let's calculate the expectation value of omega. And again, same expression, psi star times the omega operator times psi integrated over all space. And we'll substitute the psi star equal to a summation and psi equal to this summation. So that we don't get our coefficients mixed up, I'm going to label the left-hand psi with m as the summation index, and the right-hand wave function with n as the summation index. There's nothing profound, it's just so I don't lose track of what's what. Okay, so let's see how we can tidy this up. So again, we know that omega acting on f sub n, operator omega acting on f sub n, returns me little omega sub n times f sub n, because f sub n is an eigenfunction. So here I can substitute for omega sub n times f sub n. So let me do that and just tidy things up a bit. We get the sum over m times the sum over n, the c sub m's and the c sub m's are just coefficients, and the omega n's are numbers, so I can take those out of the integral, and all that I have left under the integral is f sub n times f sub n dx integrated over all space. And another nice property of the Hermitian operators that we work with in quantum mechanics is that their eigenfunctions can always be chosen to be orthogonal. And so this integral is equal to 1 if m is equal to n and 0 otherwise. This lets me get rid of one of my summations because only the terms with m is equal to n survive. And my expectation value then is the sum over the eigenfunctions, the eigenvalues, sorry, weighted by the square modulus of the coefficients of the eigenfunction in the wave function. So the expectation value in this case is the weighted sum of the eigenvalues of the operator corresponding to the observable. And the contribution of each eigenvalue to the expectation value is given by the square modulus of the coefficient of the corresponding eigenfunction in the wave function that we're interested in. So this is called the generalized statistical interpretation of quantum mechanics. And it tells us that there's something fundamentally different between wave functions that are eigenfunctions and those that are not. So that's all for today, and thank you for listening.